Okay, now, so on the test, if it didn't go as well as you would like, there was another version of the test that you can take where I do like the weighted average thing, okay? But the end of the term is Friday. So if you're gonna do that, that needs to happen like today's Thursday, like even like today after school, or might be a push, but like tomorrow morning before school, or tomorrow after school, something like that, and you can start it during encore and then finish it later. I can give you like pages of the test at a time. Again, it's not the same test, but it's pretty similar. So, fortunately, in this class, no one missed number 2. Can't say that about my first class.
Are you going to flunk those people?
So that means no one flunked, right?
Not for missing that question. You asked.
I know.
I told you. Now, on question number 8, okay? You throw a stone vertically upward and feels like, okay, once it's free of your hand but moving upward, the two forces acting on the downward pull of gravity and upward force due to its motion. Okay? It's up in the air. You have no contact with it. What's the only force acting on it?
Gravity.
Gravity. Okay? That's it. Okay? It's not in contact. Now, does it have inertia? Yeah. Does it want to keep moving up? Yes, but inertia is not a force. Okay? The only force acting on this thing is gravity. That's it. There's nothing else. On. Now, on 10, why is the acceleration 0?
Because the force of friction is great.
Yeah, your frictional force is bigger than your applied force. It doesn't move. Okay? Your frictional force is 25 newtons. You're only applying 20 newtons to it. It doesn't move. Odd. Now, the question on, it was number 3. The force that creates friction is and a lot of you said it was gravitational force. Look, if you're in deep, deep space, okay, where the effects of gravity are neglected, if you rub your hands together, do you still think there's friction? Yeah. Okay? Yeah.
The gravity between them.
Your body creates its own gravity.
Yes.
No.
What? Oh, a little hand jive.
Dude. No. Okay. Now, the reason I put on question number 14 is because if you ever watch like Star Trek or whatever, they go to like warp speed and like they snap their fingers and they're at warp speed. Well, the reason I had you kind of do that computation is that you're trying to get, and this is just like 10% of the speed of light. And this is an acceleration of 11.2 meters per second squared, which is still more than what you're feeling now. It would take you 31 days just to get to 10% of the speed of light. Not boom, you know? So it's like, oh, physicists look at that going, oh, no. The acceleration would be so great you'd be a pilot with you at the back of the ship. Okay. 18, 19, that all went pretty well. 20 was a bit of a train wreck, but let me kind of explain how I tried to grade 20. There was kind of 3 distinct parts to it: the net force, the acceleration, and the time. So here's where the wheels kind of went south. So you were sitting here, and here's the cart, right? Okay? Now, regardless of anything else, the magnet, anything else, if you set that cart on the inclined plane, what's it going to start to do? Roll down. Why?
Gravity.
It's gravity. Oh, little force parallel action, okay? Which is mg sine theta, and we're going to make that negative because that's 0.314 newtons. You do the math, this is what you're going to get. So then you've got this mass out here, right, which is 20 grams, and you divide that by 1,000 and multiply, you get 0.196 newtons. Okay, so I've got this force pulling it down, and this force pulling it up. Okay, cool. But then you've got the magnet. So here's the deal. I tell you, this thing is going to accelerate down, okay? What does the magnet always make you do? Speed up or slow down?
Slow down.
Slow down. It's a braking force. It's an opposing force. So that magnet is going to provide a force that's going to be acting upwards to oppose that motion. So you've got these two forces acting up, 0.196 and 0.088, and you've got this force acting down. So basically it's this plus that, there's your net force. Now, this is a situation where just read the problem in its entirety. I tell you, when you let go of it, it begins to accelerate down the hill. So what does the net force, what sign does the net force have to have? Negative, because it's accelerating down the hill. You can't make this thing accelerate down the hill with a positive net force, okay? So that's why you look at this problem in its entirety before you even start the calculation process. You go, oh, right, I've got to have a negative net force. Okay, right. And if you don't have one, guess what? It's incompatible with that physical system. 21 is a little frustrating just because I gave you an identical problem on the review with the answer key. And some of you, usually what got jacked up on 21 is that you tried to use this mass that was suspended as in terms of your frictional force calculation. Love of God, your friction is here. This has nothing to do with it. You could have an elephant suspended from the end of the string. It's only this force normal that's going to affect that frictional force. This has absolutely nothing to do with that frictional force. It's all right there. Anyway, but all in all, the test went well, and nobody missed number 2. Okay, so any questions? Going once, going twice, so give me the test back. That's okay. So on projectile motion. The beauty of projectile motion is that there really isn't anything new. We just kind of repackage some old ideas, which is what you see a lot in physics. Is like you take the same ideas, you just kind of put them in different situations. So with projectile motion, there's 2 types of generic problems. One is what we call, or I call, a lemming problem. Does anybody know what lemmings are famous for?
Oh,
Jumping
following
off
each other
cliffs.
off the death, something like that.
Off a cliff.
Wasn't there like a Disney cartoon or something about them?
Yeah, there
Where
was,
they
there was a Disney cartoon. So, lemmings are famous for jumping off of a cliff in England and drowning in the ocean below. So, just telling you. So, lemming problems are a situation where something is just projected off of a cliff, or even if I like take a golf ball and I just throw it horizontally. But here's what's important about this, is that your initial vertical velocity, VYO, is going to equal 0, okay? I'm not shooting it up in the air, I'm not shooting it down, it's just going all horizontal initially. Now, in contrast to that, you can have ground to ground problems. So this is like if you hit like a golf ball, where it goes up and comes down like this, okay? Or even if you shoot like kick a soccer ball, whatever it is. So what happens here is that you have a Vy and you have a Vx. So lemming problems, you start off, the only thing you have is Vx, horizontal velocity. With ground to ground, you have both initially. Okay, so the only thing we're going to deal with today is lemming problems. We'll deal with these tomorrow on the ground to ground stuff. So tomorrow we'll get there. Today we're just going to deal with this. So here's what you're going to see again and again and again. It sounds like an ad from Vegas. But what happens in the X, in other words, what happens in the horizontal motion, stays in the horizontal motion. So this is your mantra. What happens in the X stays in the X. What happens in the Y stays in the Y. Okay? And there the two shall meet. Okay? That's it. What happens in the X stays in the X. What happens in the Y stays in the Y. So, with lemming problems, you're going to start off and you're going to have some horizontal velocity. So if I take this ball, okay, and I throw it, as soon as it leaves my hand, okay, it's going to have some initial horizontal velocity. But as soon as it leaves my hand, what does it begin to do?
Slow down.
All
It begins to accelerate. Which direction?
down.
Downward. So here's the deal. It's subtle, but it's important. if I just drop this ball straight down, every time, what's going to be the path of that ball? Straight down, right? It's not going to curve this way, it's not going to curve that way, it's going to fall straight down. Why does it fall straight down?
That's the only direction that there's an unbalanced force.
There's no horizontal forces. This is going to be a key thing. There's no horizontal forces. It only falls straight down. Now, if I drop this thing and you see it begin to go in that direction, what could you probably conclude?
There's a force acting that way.
There's a horizontal force. There's wind, there's a magnet, you know, a random gravitational field lurking out here, something, okay? But there's something that's going to change that direction. But it's not, so it falls straight down. So here's what's going to be important. On projectile motion, we're going to assume that the forces in the x direction are zero, okay? That there are no forces in the x direction. Because think about this. When I throw this ball, we're going to assume that there's no forces in the x direction. So what does that mean in terms of the velocity in the x direction? Is the velocity in the x direction going to change?
No,
No. Why?
because it's no force.
Constant, right? No, there's no net force. So here's what's important. There are two ways to maintain a constant velocity. Okay, there's two ways. One is that you get it moving and there's just no forces at all. Okay? Inertia keeps it moving. That's one option. You just give it a throw and it's moving and that's it. Okay? There's just no other forces. The other option is that if I've got this hockey puck, right, and I want to keep it moving, what do I have to do? A force, but the balance is out
Friction.
the frictional force. So there's two ways that you can have constant velocity. Either there's no force and you just get it moving, or your applied force balances out your frictional force. Now, but look at this. As soon as this thing leaves my hand, are there any other forces? Whoa. Run away, ball. Are there any other forces acting on that ball once it leaves my hand? Gravity. But are there any horizontal forces? No. So here's what's going to be important. Once this thing leaves my hand, there are no forces. I'm not going to keep pushing it, okay, because I can't, because it's left my hand. So when you have no forces, what's your horizontal acceleration going to be? Zero. Don't make this difficult. If there's no force, guess what? The acceleration in the x direction is going to equal 0 meters per second squared. Okay? Now, what's the one equation that you can use if there is no acceleration? There's one equation that relates velocity, time, and distance if there is no acceleration. No. Simpler than that.
Wait.
Is it where the v
D is equal to 1.
No. It's the simplest equation. You've used it since like 6th grade.
D equals V over T, like Landon said.
Oh.
Right? Or the correct thing, but with those things.
How about
V equals
distance
V.
equals velocity
Yeah.
times time?
Yeah.
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 That one.
Yeah, that
That's
one.
it. Okay. Now, with projectile motion, we got to kind of introduce some new ideas, but it's the same thing. With projectile motion, the horizontal distance the ball travels is what we're going to call range. Okay, it's kind of the technical term for horizontal distance. So instead of distance, I'm going to put r. Now, with this v, because we've got x velocity and we have y velocity, we have to keep track of what these are. So I'm going to call this vx time. So this is a situation of what happens in the x stays in the x. What happens in the y stays in the y. So we're assuming that there's no forces acting in the horizontal direction. Nothing. Nothing. I've got a vx. Multiply that by however long it's in the air. That's going to be the distance that it's going to travel. Okay? But this only happens in the x direction. Now, realistically, especially in Kansas where we have a lot of wind, this is not true in a real world situation. If you've ever tried to kick a soccer ball or something or a football into the wind, this doesn't happen. Okay, you get you get acceleration in the horizontal direction. Either it's going to make it, either you're going with it and it's going to carry it a long way, or it's against it and you kick the ball up and it, it just knocks it straight down. So, but the problem with that is then you get in, that gets real complicated because then you're calculating horizontal acceleration, and then you have to have like drag coefficients and aerodynamic calculations, and you have to know the wind speed and a whole bunch of other stuff. So to make it simple, we're just going to assume that the horizontal velocity remains constant. Don't fight it, accept it, it's a cool deal. Okay? Got that? Horizontal, boom. So let's say that I'm going to launch this thing at 5 meters per second. So if I were to draw a velocity time graph for the horizontal motion, what would it look like?
Horizontal line is 5.
Yeah, why?
Because there's no other force acting on it. It's
Yeah.
a constant velocity.
So remember, when you have a horizontal line on a velocity time graph, one of two things is happening. Either there's no forces on it at all, and inertia is keeping it going, which is what's happening here, or the sum of the forces adds up to equal to 0. Okay? Well, once it leaves your hand, there's nothing left in town, so this is what this is going to look like. 5 meters per second. It's going to stay at that or whatever it is. Got that? We're good. Now, I want you to pretend that none of this has happened. Okay? What we just talked about, wipe that from your mind. Well, I'll get it back in just a second, but momentarily, just act like nothing happened. So, pretend that you're back in the acceleration unit. Okay? And way back when life was simple, and at the time it seemed horribly complicated, and now you're going, oh, whoa, that was simple. Oh, we had 4 equations. Cool. Okay. So I'm going to hold a golf ball up to a height of 2 meters, and I'm going to drop it. So 2 meters above the ground, I'm going to drop it. I want to figure out how fast it's going when it hits the ground, and how long it's going to take. Okay? So don't worry about projectile motion. Don't worry about anything like that. I'm just going to drop the ball. It's going to fall 2 meters. So let's start with the velocity. I want to figure out how fast it's going when it hits the ground. So, Hunter, what equation could I use?
P equals V naught plus AT.
I don't know time. So what's the equation that doesn't involve time but involves a lot of velocities?
P equals
Let me give you your hint. It starts with v squared.
is it that equation?
That equation, right? So I've got v squared equaling v naught squared plus 2ad, right? Cool. Now, I'm just going to drop this thing. Whoop, here we go. So what's my initial velocity? 0. 0. That goes away. I take the square root of this whole thing. I get 2ad, right? Okay, old school. You should be able to do this without giving this a second thought. Oh, okay. Hey, no worries, right? So I got 2 times, technically, a negative 9.8 meters per second squared. Technically, that's negative 2 meters. So somebody take 4 times 9.8, and then the square root of that, and you're going to get 6 something.
6.26.
6.26 meters per second. Okay? And technically, that's going to be negative if you're going to pick it. All right. So that's kind of cool. Now, based upon that velocity, before I calculate my time, we'll get the time in just a second. But just knowing this number, is the time that it's going to take to fall going to be bigger or smaller than 1 second? Madeline,
Smaller,
why?
because negative 6.26 is less than negative 9.8.
Yeah, because if it fell for exactly 1 second, how fast would it be going?
Negative 9.1, or negative 9.8.
Or negative 9.1 if it was a little smaller. Let's go with negative 9.8, right? So I know my time has to be less than a second. That's what I'm saying. With the beauty of projectile motion, all we're doing is just rearranging some ideas into a new idea. It's the exact same thing. We're just building a new construct and way to look at things. So let's talk about the time. Now, I don't want to use this answer, because in case this is wrong, then my time is going to be wrong. So how can I figure my time knowing my initial velocity at distance and my acceleration? Birthday girl, what can I do? Ah, nice. Nice.
We didn't sing happy birthday, Bird. Yeah,
No, we're not singing happy.
Please, yeah, thank
we
you.
did that one
She
time.
doesn't want it sung, and I don't want it sung.
Yeah, we don't want it. So.
Yeah.
We can't.
Yeah.
Even the Christmas.
This isn't Christmas.
It's already Christmas.
Oh, no, it's not. Oh, no, it's not even Halloween. No.
You're all in, everyone.
Hey, don't break the
October,
No.
all in.
Look,
Look at all the green and red.
Okay.
Look at all the green
It's
right there,
happening.
the red
It's
stuff.
happening.
Jingle bells all the way.
Okay. All right. So, what's my initial velocity?
0.
0. Okay? So, this solve for time. Who screwed this up? Somebody screwed this up.
No one's.
Oh, yeah, when they solve for time on the test.
Oh, I did.
Oh,
It
yeah.
was me.
Great. So,
I'll never forget it now.
so what does this look like solve for time?
Okay, it's t equals radical to 2d over a.
Yes, nice. Thank you,
I wrote radical d over 2a,
Yeah.
buddy.
Good job, dude.
Okay.
Hey, but he knows it now.
So,
That's progress.
in what you'll see on projectile motion with lemming problems, these are kind of your two big go-to equations in terms of vertical motion, okay? This is going to get you your velocity, this will get you your time. So these are the two go-to equations in vertical motion. Now, here's what you have to be careful of. If you're talking that acceleration being gravitational acceleration, this is the classic example of what happens in the y stays in the y, what happens in the x stays in the x. So anytime this is g, and you're talking about that gravitational acceleration, that distance is only going to be your vertical distance, not how far it goes, okay? Not how far it goes. This initial velocity here, that's your initial vertical velocity, not like the 5 meters per second when you project it horizontally. So this is the ultimate example of what happens in the x stays in the x, what happens in the y stays in the y. So anytime you're using anything that involves 9.8 meters per second squared, the only thing that you're talking about is a vertical displacement and a vertical velocity. Nothing whatsoever to do with the horizontal motion. Nothing, nothing, nothing. All right. So let's get the time. So somebody take 2 times technically negative 2 meters and divide that technically by negative 9.8 meters per second squared. So what do you get for the time?
0.408.
No.
0.639.
What?
0.639.
Yeah, that I can live with. I'll call it 0.64 seconds. Okay? So 0.64. Oh,
Goodness.
that's off. Okay.
I
So
thought
I got
we were just doing
0.64 seconds, right? Which is 1 Mississippi. Okay, a little bit less than 1 Mississippi. 1 Mississippi is equivalent to 0.64. Okay, and that matches with what we said because we said it's going to be less than 1 second because my velocity is less than negative 9.8. Cool. Okay. Now we're going to merge everything that we've talked about so far. So visualize this. I've got 2 marbles. I'm going to launch one with an initial velocity of 5 meters per second. And it's going to go on a path like this. And that's going to fall 2 meters. Okay? So this one gets launched. We're going horizontal, exactly horizontal. Not up, not down, horizontal. At the same time, I'm going to drop another marble, and it's going to fall straight down. So one falls whoosh, straight down here like this. The other one goes out like that. So here's the question. Which one hits the ground first?
Neither one.
Or do they hit at the same time?
Ground, they both hit at the same time.
Why?
The only force acting on it is gravity. Gravitational acceleration.
What stays in the y?
Earth.
Happens
Yeah.
in the y stays in the y.
Did I say that right?
I don't know. I heard of that, and then you kind of faded off.
Yeah. Gravity.
Why do they hit at the same time? Gravity.
Yeah.
Yeah.
You don't have
Because
one force, you
nothing-
don't have
The X velocity doesn't affect the
Hold on, whoa, whoa,
Y
whoa, whoa,
velocity.
whoa, Madeline, what'd you say?
I said, but the other one goes further distance.
But the other one travels a greater distance. So maybe that one should take longer?
No.
Matt, you shake your head no.
Whatever happens in the X doesn't affect the Y, right?
Okay?
That's all I
So,
hear.
well, let's kind of look at what happens here. So I've got
Cool.
this and this little launcher up here. So, I just have to have, you know. So when I pull back the spring and I'm storing potential energy, this one has a hole drilled in it. And then when you launch it, that begins to fall, okay? Everyone needs one of these. So I'm gonna pull this back, right? Huh?
It's a lame launcher.
No, just chill out. This one's just gonna fall straight down. That's the point,
Oh, okay.
okay? God, it's a harsh crowd. Those are lame launcher. Back off.
I was upset.
Now I've got this one that's actually gonna get shot out,
Oh, sweet.
okay?
Yeah, aim it over there.
Right? So, okay. So here's the point, is that when this one gets launched, this one falls, okay? That's the idea. Now, one of the things you'll see that this is potential energy, because I've done work, I've compressed the spring. As soon as I flip this up, what is nature not like? Potential energy or kinetic energy? No. Mother Nature loves kinetic energy.
Potential.
Hates potential energy.
Gets rid of
Okay?
it.
Yeah, they had something going on Snapchat or Instagram, whatever. Somebody said something about somebody and they have never liked each other ever since. Okay? Potential energy and Mother Nature are not friends. Okay. So, Mad Max, kind of give this a shot up here.
Ooh,
So,
good. Can't hurt his camera.
I got this up here.
I don't want to zoom too much.
I know.
So, this one's gonna get launched out, and that one's gonna fall. So, 3, 2, 1. So, what happened? They hit at the same time.
Matt Bianco is a genius.
Now,
Yes, you are.
this is like the classic example of you look at what's a factor and what's not a factor. So, let me kind of clean this up. So we said that vertical velocity was 2AD, and the time was 2D over my acceleration. In any of these calculations that we've done so far, have I given you the mass of the golf ball?
No.
No, why?
Because it doesn't matter.
Could you plug the mass of this golf ball into this equation at all?
No.
No. I don't tell you that it's a top flight or that it's orange or that it has 182 dimples in it. Okay? Doesn't matter. It's not a factor. So when you look at that calculation of time, what's the only factor that determines how long this thing is in the air? Acceleration due to gravity and what? How far it falls. The fact that this one has a horizontal velocity of 5 meters per second, can you plug that into this equation at all?
No.
No. That's why they both hit at the same time. Now, does this one travel a greater distance? Yes, it does. Okay? But what you all said, like Matt said, what happens in the X stays in the X, what happens in the Y stays in the Y. So, in terms of gravity, gravity says, hey, great, I'm happy for you. You got a 5 meter per second. You aren't you special? Okay? I'm still going to make you hit the ground at the same time. Okay? So it isn't like having a horizontal velocity is like this anti-gravity shield, and, oh, gravity doesn't affect you as much. Okay? It's still going to make you fall. Now, would there be aerodynamic effects, like if you take a piece of paper and make it into a paper airplane and you throw it horizontally? Okay? Yeah, that's a whole other ball game. Okay? That is a whole other ball game. But if you're just talking two objects that aren't shaped like paper airplanes, they're both going to hit the ground at the same time. So, Vx is not a factor. So the only thing that you need to know to figure out how long something's in the air is how far it falls in the acceleration. If you want to know how fast it's going vertically where it hits the ground, you only need to know how far it falls and your acceleration. That's it. The mass, the Vx, all of that is not a factor. It's not there. You can't plug it into that equation if you tried. It's not there. But an interesting thing happens. So let's look at this equation for time first. So initially we said we were at 2 meters. And we used time, square root of 2 times 2 meters over g. And we got, what was the 0.64 seconds. Okay? Now, here's the question. If I doubled that height to 4 meters, would that double my time? McGriddle, you shake your head no.
Correct. I don't think it will.
It's falling twice as far. Yeah, but
Gravity accelerating more over a distance.
gravity is accelerating it more.
Over the distance.
So
Like it builds up.
it builds up. What is it?
The acceleration.
It builds up.
Yeah.
So the acceleration gets faster as it falls.
Yes.
I think you mean velocity.
Oh, the velocity. Yeah. I meant velocity.
I understand.
You know where I'm going.
No, I don't. Sure, I have no idea where you're going. Okay. Let's just crunch the numbers. Okay. Let's do what we call smash mouth physics. So in smash mouth physics, you actually go through and you recalculate. So to take 2 times 4 meters. So great, take 2 times 4 meters and divide that by 9.8 meters per second squared.
0.903.
0.90. So even though I doubled the distance, did I double my time?
No.
No. Okay? So let's talk about why, right? Let's talk about why. So there's a couple of ways you can approach this. One's kind of an elegant way. If you look at your generic equation, that's 2d over g. So this is my initial calculation of time. Okay? It's just some distance. I don't care what the distance is. I don't know. It doesn't matter. But then if you look at what's going to happen differently, my new time, which is what we call t prime. Okay, so this is going to be like the new time. Well, what do I have to do to distance to double it? Don't make this complicated. What do I have to do to double my distance? Multiply it by 2. Oh, okay, right. That's 2d over g. Now, for those of you that have done a lot of math, which is everybody in this room, can I rewrite that as the square root of 2 times 2d over g? Can I do this? Legal? Hunter, what's your gut feeling? If you're the algebra police, can I pull this off? Yeah, okay? It's all underneath the radical. All I did is pull this out. Now, so, great, humor me. Take the square root of 2 and multiply that by 0.64.
0.905.
You get the exact same number.
Yeah.
Okay? So when you double something that's underneath the radical, you don't double it, you increase it by the square root of 2 because it's underneath the radical. Okay? Now, what if I increase the distance by 4? What if I went from 2 meters up to 8 meters? Then what would happen to the time?
Double. You would double.
Then it would double what?
Because the square root of 4 is 2.
Beautiful. So if I want to double the time, I'd have to increase the distance by a factor of 4. If I wanted to triple the time, I'd increase it by a factor of 9, because it's underneath the radical. Okay? Got that? So anytime something's underneath the radical, doubling it doesn't double it, because it's underneath that radical. Now, let's talk about velocity. So the velocity, we said, was 6.26 meters per second. So the same thing is going to happen here. If I look at my new velocity, I've got 2 times g times, in effect, 4 meters. Well, look, if this was underneath the radical, and I doubled it, and it increased by the square root of 2, if I increase my distance, what's that going to happen to my vertical velocity when it lands? It's also going to go up by the square root of 2. Okay? So anytime something's underneath the radical and you double it, you alter it by the square root of 2. Good with that, Mary?
Yes.
Birthday girl, are we good?
Yeah.
Okay, all right. Okay, so if you double your age and it's a square root function, you know, it only goes up by the square root of 2. Okay, cool with this. Now, so let's look at that ball, kind of tie everything together. So here's this one, it's going to fly through the air, it's going to land down here. As it falls through the air, what happens to that horizontal velocity?
It stays the same
Why?
because there's no forces acting on it.
No forces, it's going to remain as a constant 5 meters per second. Cool, right? 5 meters per second. Now, my initial vertical velocity, Vyo, is going to be 0. As it falls, does it accelerate vertically?
Yes.
Because that's the only way we have an unbalanced force. So as it falls, now McGriddle, as it falls, what happens to my value of my gravitational force?
Gravitational force stays the same, but velocity increases.
Ah! Nice. So, what's the value of the acceleration caused by that unbalanced force?
What?
What's the value of the acceleration?
Negative 1.80 meters per second.
Nice. Okay? Is that going to change, McGriddle?
No.
No, that's going to stay the same. Now, when this thing lands, okay, and this is where you have to pay attention to the terminology. When this thing lands, it's going to have a horizontal velocity of 5 meters per second. But it's also going to have a vertical velocity of 6.26 meters per second. So, what you can find is the speed of the ball. So the speed of the ball is going to be the resultant of your horizontal and vertical velocities. So what that means is if you could sit down here with a little radar gun, okay, that radar gun is going to tell you what the speed is as a resultant of this 5 and that 6.26. So this is where we're going to harken back to vectors. If this is 5 and that's 6.26, how can I find that resultant?
Tip to tail method.
Well, that's what we got drawn out, but how can we actually get the numeric value of that?
Pythagorean theorem.
What'd you say?
Pythagorean theorem.
Pythagorean theorem, okay?
8.0.
They're at right angles. So what'd you get?
8.01.
So about 8 meters per second, okay? So what that means is that if you were sitting down here with a little radar gun in the ground and shot it up, right as that ball hit, you would get a reading of 8 meters per second. But it's a combination of a horizontal velocity of 5 and a vertical component of 6.26. But if you had that radar gun up here, it would only read 5 meters per second because that's how fast it's going when it's initially launched. So as it falls, your vertical velocity is bigger and bigger and bigger. That's why this turns into a parabolic path and not like a triangle. This thing doesn't go out and go, whoink, okay? This is why it travels in a parabolic path. Good with that? Got it? Okay, so stop that.
Voted, but.
Okay,
Can we just do thought experiments?
so what you're going to do in the lab, you're going to take this little ramp,
Oh, there's a.
like such, and you're going to clamp that to the edge of the table, oddly enough, with a clamp. Again, first block kind of struggled with that concept. So,
Tired dummies.
they're half asleep.
Hey, I'm having some too.
Probably shouldn't have said that, Eli.
Okay? So, you're going to take this little marble, and you hold it up here. What type of energy do you have when you hold it up here?
Potential.
Potential. As soon as you let go of it, potential changes into kinetic. Because Mother Nature hates.
Potential.
Yeah, and it isn't like you let go of it, Mother Nature goes, I don't know, maybe I'll give it potential energy a second chance. Maybe I judged it too harshly. No! Okay? That die has cast. That ship has sailed. They're never going to like each other. What? So, I'm just telling you, it isn't a bad thing. So, you're going to start up here, you're going to roll down, right? So, when goes, you'll notice that this section of the ramp is horizontal. Oh, so when it leaves the ramp, what's its vertical velocity?
0.
0, because it's going to go horizontal. That's kind of cool. So, in terms of the lab, the only thing we're going to worry about is what happens when it leaves here. I'm not worrying about what happens up here. This is just creating the horizontal velocity. That's all that's doing. So it's going to go out and it's going to go doink, okay? So here's the 2 bits of information that you need. You need to measure the height that that's going to fall, okay? So you're going to have your vertical distance, right? Then you're going to need to measure the range and how far it goes. So to do that, we've got this little kind of cool invention called carbon paper. And so if you put that down, so what you're going to do is you're going to roll it down once, and you're going to get an idea of how far it's going to go. And you're going to go all the way down to the ground, okay? You're going to go, like, you're going to have it on the lab tables and go all the way down to the ground. So get an idea of where it's going to land. Then you're going to take a sheet of paper, put that down where you think it's going to land, put the carbon paper over it, okay? And the carbon paper, make sure the diamond side is up. So then when that marble lands, then what will happen is that it will transfer through a mark onto this paper. So this is actually, it used to be in the Stone Ages when dinosaurs walked the earth, and there were like typewriters, and they were mechanical typewriters, even worse. So like there weren't printers. Like if you wanted to type the letters you would take THE and these, and it would, there was a lever that would come up and it would show up as THE, okay? There was no like time delay and you could print it out later. I mean, it was real time. But if you wanted to make a copy of it, and this is where carbon copy comes from on email. So what you would do is you would have the letter, which was your original. Then you'd have a piece of carbon paper like this behind it. And then you would have a second letter back here. So then, when mechanically come up and strike the first page, the original, then it would transfer that image to the second page. And this is called the carbon copy. And so that's when you look at email and it says CC, that's what that stands for, is a carbon copy. So if you send that, okay, so little history, yeah. And you might have like 3 or 4 pages. And that's what, and then at the bottom, you would type who else is getting this letter. You know, like if I were sending it to Dr. Higgins, but I also wanted Dr. Boss to get it or whoever, I would say carbon copy, you know, Dr. Higgins, Dr. Boss, so everybody would know who else was getting a copy of that letter. But that's what that CC stands from, is from carbon copy, because it was a mechanical transfer of that image to the second page. Okay, so in terms of the data, here's all the data that you need. The height of the table and how far it goes. Don't ask me for a stopwatch. I'm not going to give you one. You're going to calculate the time, okay? You're going to do everything else. Now, when you get on those calculations at the bottom where it says V resultant, what I want there is that when this thing lands, it's going to have a horizontal velocity that you're going to use, and you're going to use range equals Vx time. And then you're going to have a vertical velocity, and you're going to use that V equals the square root of 2AB. And you're going to find that resultant of the two. This is the angle that I want. And don't worry about making it negative and subtracting it from 360 and all this good stuff. It's all I want. Just make it simple. Just give me this angle. It's probably going to be around 70, 75 degrees, something like that. Okay? So, when I want this angle, this is the angle that I want. Don't make it complicated. You know the side opposite, you know the side adjacent, little inverse tangent, boom, you're off to the races. Now, when you get on the backside, and yes, it was the backside, when you get to question number 1, you got a car traveling 112 kilometers per hour. What's the first thing you need to do with 112 kilometers per hour?
30 meters per second.
Yes, multiply by 10 and divide by
36.
Beautiful. Okay. Now, you need a bunch of calculations, how far it's going to land, all this good stuff. When in doubt, draw a picture, because what happens on projectile motion problems is that you screw up your x direction with your vertical direction. Take a second, make a simple sketch, okay? Now, then down below I said if the horizontal velocity was doubled, how would each of the following change? And don't tell me, oh, it's going to change too. No, okay, this isn't some feel-good political ad. I want you to tell me exactly what's going to happen. An increase or decrease is not going to cut it either, okay? So you're going to tell me, oh, it's going to double, it's going to triple, it's going to increase by the square root of pi. So if you want to go with a pure analysis of it, you can do that. Now, if you want to do the smash mouth physics thing and actually go through and recalculate everything, you can do that as long as you give me that answer. So I don't care how you do it. The more elegant approach is if you actually like kind of look at it and go, oh, like for example, if you have range equals Vx time, think this through. If I double my horizontal velocity and I'm in the air for the same amount of time, what's that going to do to my range?
Double it.
Or double, because this is just Vx time. But it isn't, but if it was the square root of Vx time and I double Vx, what would happen to the velocity, or what would happen to the range?
Who multiplied by the square root of 2.
Then it would go by the square root of 2. Okay? So if it's just Vx time, I double this, hey, my range doubles. If it's underneath the radical and I double it, it goes up by the square root of 2. Just something to think about. Okay. On all of these, you have 3 significant digits. I want all your answers with 3 significant digits. Go lab freely.